Good afternoon, everyone. Welcome to MIT.nano's Fall Seminar Series. It's wonderful to have everyone here. It's a pleasure to start this year's seminar series with a talk by Professor Debbie Ceneski. Professor Ceneski is an associate professor at Stanford University in the Aeronautics and Astronautics department, and by Court C, the Electrical Engineering department. She also leads the Extreme Environment Microsystems Laboratory at Stanford, as well as is the site director for the Nano at Stanford program, as well as co-editor for the journal Sensors and the IEEE Journal of Microelectromechanical Systems, JMEMS. Debbie's research interest includes development of nanomaterials for extreme harsh environments, high temperature electronics, as well as robust instrumentation for Venus exploration. Professor Ceneski's research has been recognized by many awards. She has been the recipient of the Emerging Leader Abby Award from AnitaB.org, the NASA Early Faculty Career Award, as well as the Alfred Sloan Foundation PhD Fellowship Award. Before I turn it over to Debbie, I just would like to remind our audience that you can ask your questions either by typing them through the Q&A option of this webinar, or you can wait until the end of the talk and raise your hand and directly ask your questions. So with that, Debbie, it's a pleasure to have you here, and I turn it over to you to learn more about your work on nanoelectronics for extreme harsh environments. Thank you, Debbie.
Thank you. Thank you so much for the introduction, Farnaz. It's great to give this presentation virtually and maybe one day in the near future in person. So today I would like to discuss tiny but tough nanoelectronics for extreme harsh environments. And what I'll cover is my group's recent work in the area of gallium nitride and really cover our trajectory since I joined Stanford about 9 years ago. And also talk about some new projects that we've been working on in the area of graphene-based materials and devices. So this is an image showing a vision for the future, Internet of Things, and potentially you can use semiconductor materials such as gallium nitride for the development of Internet of Things devices. And so the idea is that you would potentially instrument industrial machines such as gas turbines used in power and propulsions, bridges, our automobiles, our roads, for example, instrument them with sensors, and there would be a stream of data coming out. And using big data analytics or machine learning, we can react to this data on demand. We can potentially visualize it with our remote systems, such as our cell phones, and then also react on demand using our physical human networks, such as the internet. And of course, store all of this information on the cloud. And this could potentially translates to billions of dollars in savings in the way that we utilize and operate our industrial systems. One challenge in this vision of, again, the Internet of Things or IoT is that many of our power generation and propulsion systems have harsh environments within them. And so this is a slide I show in most of my talks. I designed this slide when I was a postdoc at UC Berkeley, when I was sitting and really thinking about some of the applications for some of the extreme environment microsystems that I was developing. And so these are the applications that have really supported and the work that I've conducted over the years. So downhole applications such as geothermal, and then also oil and gas exploration. Also energy production via industrial gas turbines, and then propulsion systems such as automotive engines and aircraft engines. So as you can imagine, within these systems, there's harsh environments, right? We have supercritical water, we have hot crude oil, we also have combustion. And so how can we realize this vision of, smart on-demand and creating autonomous systems through data collection? It's really challenging because of the temperatures, the pressure levels, and also the harsh chemical constituents. So our traditional sensors and semiconductor materials that we have at our disposal, they unfortunately do not function in these environments. So we have to look to new types of materials. And so another application space is high frequency and high power devices as well, or applications. So this is really looking at materials beyond silicon, our traditional silicon, to meet the high power density requirements and the speed requirements for emerging applications. And so often we turn to wide bandgap materials such as silicon carbide and gallium nitride to meet those needs. And so one vision of the future is, can we place, again, wide bandgap materials such as gallium nitride and or silicon carbide within our machines of the future? So this is, let's say, an electric aircraft. It has a motor drive system that would be run with, again, these high power, high speed electronics. Unfortunately, in the design of many of our transportation systems, we have to use cooling loops. So this is relevant in electric cars as well. A lot of the payload that goes to our cars, such as the electric Tesla automobile, is the cooling loops. So there's first stage and second stage cooling loops, and that are required so that our electronics and our batteries can work well. Maybe one day we look to these emerging semiconductor materials so that we can eliminate these cooling loops and reduce payload. So how are we going to create these robust Internet of Things or high power or extreme environment electronics? When I was joining Stanford as a young faculty member, I read lots of papers in the area of gallium nitride. So this was published in 2012, just when I was joining, and showing extreme temperature operation. So this is a 1,000 degrees Celsius gallium nitride high electron mobility transistor. So the chuck here that you see glowing is 1,000 degrees C. And also something to note here is that the ambient is vacuum. So it actually doesn't capture a lot of the potential oxidation effects that you might encounter in some of the environments that I mentioned previously. So some of the work that we've done to advance this technology is study new operating environments that are oxidizing and also chemically corrosive. And so this is nonetheless really remarkable results showing, again, 1,000 degrees C operation, so gate current up to 1,000 degrees C, room temperature operation, and then cycling as well. And so this is here evolution of the gate current as you continue to conduct these heat tests. And that's something that's very, very important, which I'll touch on throughout the talk. Is that it's not only the temperature, but the duration and also the cycling of the temperature that's important to understand the longevity of these kinds of materials. And so I was really intrigued by this result, right? That you can make an actual transistor that isn't super, super leaky. There's some leakage, of course, that we can see, but it continues to function at such extreme temperatures. And so I decided to really look deeply at gallium nitride even further. And so what stands out to me, this is just a table summarizing the properties of gallium nitride in comparison to other wide bandgap semiconductor materials and also silicon. And so what stands out to me is the melting point, so 2,500 degrees Celsius. And this is due to the tight binding energy between the gallium and nitrogen atoms. It takes a lot of energy to break apart those atomic bonds. And also the energy gap, the wide band gap. So in comparison to silicon at 1.12 eV, The band gap is 3.4 eV. And so this translates to thermal operation above 1,000 degrees Celsius, as was shown previously. That's due to the band gap. Whereas silicon, if we operate at temperatures above around 250 degrees Celsius, we start to see thermal runaway. So thermally generated carriers dominating the electrical properties. And so that really limits, again, some of these extreme environment applications that I mentioned previously. And some other attributes, the critical field that translates to high power operation, of course, high acoustic velocity, that's fairly high. And so this can translate to high frequency devices, and also the chemical stability as well, which I'll touch on throughout the talk. And so gallium nitride lends itself to, potentially extreme environment operation. And this is a material that's being developed by other application spaces as well, primarily the power and RF industry, and also the optics community as well. So light emitting diodes, optoelectronic devices. This won the Nobel Prize in 2014 in physics for the blue LED. Other application sensors, solar cells, the highest efficiency solar cells have a layer of gallium nitride within them. Also, RF resonators, we can harness the piezoelectric properties of gallium nitride to create oscillators and vibrating mechanical machines. And folks are also looking at nanostructures. So there's multiple communities that are advancing this material platform. And so what I want to touch on is also the difference between gallium nitride's transduction in comparison to silicon. So silicon is our mainstay material that we have been developing for over 30 years. And so gallium nitride is a little bit different. So it doesn't use dope junctions, which can offer advantages actually at elevated temperatures. So what we use is something called the two-dimensional electron gas. And so this is formed by two phenomenon, the spontaneous polarization. So if I look at a unit cell of gallium nitride, it has asymmetry. And so there's a dipole that's present in a unit cell crystal. And then also it's piezoelectric polarization. So if I grow a slightly doped variant of gallium nitride, let's say AlGaN, aluminum gallium nitride, on top of a gallium nitride lattice, due to the lattice mismatch, this AlGaN layer is in tension. And the combination of these two effects actually leads to the formation of the two-dimensional electron gas, this two-dimensional sheet of electrons. And this is how we transduce. This is the conductive channel that we can manipulate with external stimulus or our gate, changing the sheet density, et cetera. And this is a very high mobility or fairly high mobility channel. And you can see again this quantum well forming due to these two effects. So this is different from a doped silicon junction. We have this two-dimensional nature, which I find interesting because that can get around certain bulk scattering effects, which can really impact high temperature behavior. And so using this device architecture, folks have been maturing the high electron mobility transistor. This is an image from a commercial vendor on semiconductor where they grow these super lattices on top of a silicon substrate, so silicon 111. First, you have a nucleation layer, then you have this super lattice or buffer structure where we slowly change the gradient in the doping or create a gradient in the doping. And that helps with strain transition because if you grow gallium nitride directly on silicon, there's cracking that can form. So this is really strain engineering of these films to prevent cracking. And then you have your device layers up on top. And the traditional transistor structure looks something like this. You have your source, gate, drain, passivation, which is typically silicon nitride, although other oxides can be used as well. And then the gate is changing the sheet density of our, again, two-dimensional electron gas. Okay, so that's the device architecture. And using this platform, my group has developed high temperature capable gallium nitride transistors. So this is an image of the high temperature probe station in my lab. It operates up to 600 degrees Celsius. And something to note is that we often characterize our devices in air, okay, as opposed to vacuum. And then we study the evolution of these metals in this hot oxidizing environment. This is one of our earlier iterations of our hemp transistors, where we're using metal insulator Schottky contacts. So this is the IV response, room temperature up to 600 degrees Celsius in air again. And so this is continuing to function. These were short duration tests for some of this preliminary work back in 2016. And since then, we've done a lot of work to improve gate leakage, also changing out the gate contact, which I'll show you later in the talk. Something that happens at elevated temperatures is also strain relaxation. I told you how the hemp technology is based on the piezoelectric formation. And so straining of this, again, algan layer on top is very important. But when you start to heat up the device, you also can strain the device. And really what's important is the stacks that you use. And so what we see here is gate leakage can increase significantly depending on the type of materials that you use. And so we've done a lot of studies in that area. But leveraging this material platform, we can create a multitude of devices. And so we often call this monolithic integration. And so this is a platform that we've developed over the last 9 years, I would say, where we're again growing algan-GaN heterostructures on top of silicon wafers. And we conduct these, we call them mega run fabrication processes. So using this single wafer, usually fabricated on a 4-inch wafer, students in my group will get together and figure out, okay, what kind of device do I want to design? So this is just a highlight or a snapshot of some of the multitude of devices we've made. Pressure sensing, photodetectors, Hall effect sensors, and also thermoelectric devices. So you can have sensing devices, energy harvesting devices potentially, and also our circuitry that would interface with our sensors as well, all fabricated on this same wafer. And so what I'm going to walk you through now is really some of our recent results in creating these gallium nitride-based transistors and sensors. And this is the process, the typical process that we use. Again, my PhD was in the area of microelectromechanical systems. So I'm often interested in removing the substrate and seeing what kinds of devices we can make. And it's been really fun to explore gallium nitride in this way. So our process is different from a traditional transistor process, but we do start with the algan-GaN substrate on a silicon wafer. We often have our backside etching or windows, so we can remove the substrate depending on our process. Sometimes we do a top-down removal as well. And then what's also special about our process is our high temperature ohmic contacts, and then also our high temperature Schottky contacts. Passivation, we commonly use aluminum oxide, and then we have our interconnect metal And then again, removal, depending on the type of device that we're making, we remove the substrate so we can have freestanding structures. So this is an image of our pressure sensor prototype. So these circles here, these are diaphragms, and our HEMPs are circular shaped, and the gate sits near the edge of the diaphragm. And so what's happening is when we apply pressure to the diaphragm displaces, and we're actually applying an external strain to the high electron mobility transistor, and that's how we transduce. We convert the application of pressure to a strain to the HEMT through the diaphragm, and then we measure the IV response. And we do all of this in air at elevated temperatures. So this was work using this stage here, this little chamber here, Lincoln chamber, where we can do in situ heating and application of pressure. So this is room temperature up to 300 degrees Celsius. And we can see again, there's in this iteration of devices, we have some leakage occurring. And later subsequent devices, we were able to reduce the leakage significantly, but nonetheless, a high temperature operation. And then taking these circular HEMPs positioned on a diaphragm, we can apply pressure, and we can see that there is a change in the IV response. And so there's kind of this spreading out, right? An increasing drain current at specific voltages as we increase the pressure. And what we find is the sensitivity is actually improved when we approach the threshold voltage. And so we map out the IV characteristics plus the pressure characteristics on our to gain a pressure sensing device. So another device that we've developed, another type of transducer, or again, sensing device that can work in concert potentially with a pressure sensor, is a Hall effect plate. So Hall effect is a mechanism that is often used in silicon devices. You carry them around you in your phone. Oftentimes we use dope junctions to make a Hall effect. Basically what's happening is that in the presence of a magnetic field, if I apply a bias to one set of electrodes, due to the Lorentz force, we get bending of the electrons, and we can measure that sensitivity with a secondary set of electrodes to measure the Hall voltage. And so what's different about our device is that we're now, instead of a doped silicon junction, we're actually using our two-dimensional electron gas as our sensing layer. Okay, and so this is the conductive channel that we're using, and this is a chip showing numerous Hall effect devices fabricated on a single chip. And these can be deployed into various electric systems that might have current carrying conductors or magnetic fields. So we can measure both current or magnetic field. And this was work looking at potentially creating sensors for power inverters and motor systems and transformers as well. So what happens when you make this type of transducer, as with most sensors, is that you often have these sensor anomalies. One in particular is offset voltage. So what that means is in a zero bias, so when you have zero magnetic field, you actually are getting a voltage that's present, and that's due to anomalies in the sensor design. So this is something that you want to cancel out. And so we do that at the circuit level. We utilize something called current spinning, where we're basically averaging the Hall voltage using these 4 contacts, and then also changing the direction of our applied field. We can average that out, and then now in a zero magnetic field, we can have a zero crossing. relatively. So there's still some offset here. So we can compare that to silicon device. So this is the supply voltage. And we were at this point looking at two different versions of our Hall effect device using AlGaN-GaN and also indium aluminum nitride, which I'll start to talk about more throughout the talk. So indium aluminum nitride is a lattice match version of the heterostructure, also high mobility and high sheet density as well. And so in comparison to a silicon reference, you can see the offset of our Hall effect devices is much higher in comparison to our two-dimensional electron gas or hemped type structures. And what we found through Karen Dowling's work is that silicon devices have, again, this doped well, and there's actually thermal gradients due to this implanted well, right? It's not a confined portion in which you're creating this bias. And silicon actually has quite a significant Seebeck effect. So if you have thermal gradients across your device, you will have some voltage that's generated, and that is what is a major contribution to the offset, but also self-heating and resistance asymmetry as well. You have to make sure you have good alignment when you're fabricating your devices. And so what we studied with IR microscopy is the thermal gradients across our different generations of our devices. This is first gen where our contacts were not very well aligned, and we can see here a larger thermal gradient. This is shown in the blue, so larger DTs across our device, and that's translated to higher offset. Gen 3, we perfected our alignment, a better alignment, but still there is some, it's hard to see in this image, but there's still some thermal gradient across the device. And that again translates to the offset. But nonetheless, in comparison to silicon devices that, again, suffer from Seebeck effect, we are dramatically reducing this residual offset. And again, we attribute that to, again, reduce thermal gradients and also reduce impact of the Seebeck effect in our Hall effect devices. So we've also operated these Hall plates at elevated temperature. So there's again our two iterations, our indium aluminum nitride on GaN and our aluminum gallium nitride on gallium nitride heterostructures. And so this is work from Hannah Albert, recent graduate from my group. What she was doing is operating at elevated temperatures in air and also ramping up and down. So you can see here heat cycling up and down, room temperature up to 600 C. We see this exponential decay. This actually corresponds to a decay in mobility, which is something that is very typical for most semiconductor devices, right? As you increase temperature, your mobility goes down. And so that translates to our voltage scale sensitivity very nicely. So that's not something, that is something we expect. And then she's continued to ramp up and down. And we can see that these curves overlap with each other. And so there's repeatability, and we can see that we are actually, due to these thermal cycling, not showing any major degradation in our devices. And that tells us that our ohmic contacts are very stable, because this is a device that uses ohmic contacts. We haven't really introduced the Schottky contacts yet. I'll talk about that in a moment, but we're really happy with this result. Again, thermal cycling, I would say these are minutes of cycles, right? We haven't quite done hundreds of hours yet on this particular device in that work, but later on we have done more extensive studies, and that's something that's ongoing. So I mentioned the Seebeck effect, right? We're trying to get rid of this Seebeck effect. We want to minimize the offset voltage. But the Seebeck effect is also something you can use to create energy harvesters. So another type of device that you can make with these gallium nitride two-dimensional electron gas is a thermoelectric device, or you can also call it a heat flux sensor. So what we have done is we tried to understand, again, these heterostructures. How can we now, instead of dissipate the heat, what if we want to confine the heat in certain regions? Certain trade-offs in thermoelectric devices are the thermal conductivity and the electrical conductivity. These are trade-offs. Usually when you have high electrical conductivity, you have low thermal conductivity, and they're fighting against each other when you're trying to make these energy harvesters. So what we found is if we can change the bulk GaN, or the gallium nitride layer, which has high thermal conductivity, and we make it to a thinner gallium nitride layer, we can introduce more scattering effects and actually reduce the thermal conductivity. But at the same time, because of the 2D nature of the 2DEG, we can maintain the electrical conductivity. So we can think of this as tuning the thermal transport and maintaining the electrical transport in this heterostructure. So this is measured ZT coefficient, room temperature up to around 300 degrees Celsius. So we can see an increase in the ZT using the thin GaN architecture. And so we measured this using this suspended AlGaN-GaN membrane, again, using MEMS fabrication processes. So you can kind of see this rectangle here. This is a punched hole that's released from the substrate. So that is the hot side of the thermoelectric device, and then you have the cold side on the substrate. So using the silicon substrate to kind of as a heat sink, so you can have a delta T across the thermoelectric sensor. And then we have these little resistive heaters. These are our hot source here. And so we're creating a delta T across the two-dimensional electron gas, and we're measuring fairly high power factors on the order of 4 to the 7 milliwatts per meter Kelvin squared. So now I want to shift gears a little bit and talk about some of our space exploration activities. So we have been working on a program along with other researchers funded by NASA called the HOT Tech program. So Hot Operating Temperature Technology. NASA is interested in placing a lander on the surface of Venus. So Venus is our neighboring planet. It has a very similar mass and size as Earth, so similar density. It was said that it's Earth's sister planet. However, if you look at the environment, it is very different from Earth. The surface temperatures are 480 degrees Celsius. You can kind of see this crusty, volcanic-like surface. If anybody has gone to the Big Island and visit Volcanoes National Park, you can see here, it looks very similar to that. And also looking at the atmosphere, this kind of yellow haze. So the atmosphere is composed of supercritical carbon dioxide and also sulfur compounds. So this is a very chemically corrosive and also hot environment. This is an image of the surface from 1982 from a Soviet lander. And so we haven't had a lander style mission in close to 40 years. And so NASA and other researchers, including myself and folks also at MIT, Tomas Palacios has also been a part of this program to create extreme environment electronics that would enable a lander style mission. So we've done a lot of work studying materials such as gallium nitride for such lander style applications. But some of you might know, any space fanatics out there might know, we did win, not me, not us, but the community won 2 missions to Venus, atmospheric base, where you're doing remote sensing, Whereas some of the work that we are interested in doing is lander style missions. And the goal would be to create a 2-month video studying the weather patterns and also other aspects of the surface of the planet. Okay, so to advance technology for a potential Venus mission, the semiconductor alone is not going to solve all of the problems. So I've mentioned throughout the talk certain degradation modes. So there's strain relaxation and also degradation of the metal contacts that sit on the gallium nitride, in particular the ohmic contacts and the Schottky contacts. All of these things have to work together in these harsh environments to have a reliable transistor and really electronic platform. So it's not only the transistors, it's the circuits you want to make from the transistors, the sensing, and such. And so we need to have these fabrication elements really pinned down. So looking at the literature, there's all kinds of things that can go wrong. This is things that we've observed over the years as we've developed our fab process. So, in the early days, we started with nickel gold, our common Schottky contacts again, and we saw these bubbles that were forming, and we attribute it to nickel gold interdiffusion. Other groups have shown balling up of metal contacts and also interdiffusion of ohmic contacts into the gallium nitride. So it's important to know the evolution of these contacts in the same environment and also the same duration of the expected mission. So these are some of the work that we've done and also other folks as well. I haven't updated this table in a while, but back in 2014, we showed that our titanium, aluminum, platinum, gold technology resulted in fairly low sheet contact resistivity and also very stable resistance this was around 10 hours at 600 degrees Celsius. Since then, we've done much longer tests. And we've also started to look at titanium, aluminum, molybdenum, gold. Happy to talk with you. These are really our common ohmic contact schemes. And then more recently, we've been looking at the gate metals as well, which I'll touch on in a moment. But as part of the NASA Hot Tech program, something that we've been working on, this is in collaboration with Mina Rezida at JPL, gallium nitride surface acoustic wave resonators. And so this is an important piece of, again, maybe an IoT type device, right? This is an image from a NASA report. Sensors, different types of amplification electronics, logic. We need power, we need to store the data, and then we also need to transmit the data securely, this precious scientific data. And so one way to create a transmitter is through something called an oscillator, and this can be done in a mechanical way through something called a resonator. And this would be harnessing the piezoelectric properties of materials such as gallium nitride, where you would, again, as you apply a voltage, you would generate a displacement in the body. So these are metal interdigitated fingers that are actually formed by two ways. We can just put metal on top, or we can actually use the two-dimensional electron gas as the conductor, and we can induce an acoustic wave in the gallium nitride layer and measure the response, the frequency response. So we've done a lot of work. Mina is a resonator guru. She's made all kinds, surface acoustic wave, bulk acoustic wave, and we've applied our fabrication processes and high temperature characterization to understanding these in Venus-like environments. So this is our high temperature probe station. We use these tungsten RF probes. And so at increased temperatures, we can see a degradation or just a shift in the center frequency of these surface acoustic wave resonators. Then we also see a degradation in the Q factor as well. So there's some energy loss, but nonetheless, these guys work in air at such elevated temperatures. And then something we measure at elevated temperatures or at various temperatures for resonators is the temperature coefficient of frequency, how that frequency can drop or some materials increase with temperature. So what we're gearing up to do and what we've been doing, I don't show all the data here, but happy to share with anybody who's interested. We've looked at C doping and silicon doping and the influence of the gallium nitride doping on the temperature coefficient of frequency. And then we're also gearing up to do temperature compensation. So the turnover temperatures are at low temperature for our current architecture, but introducing materials such as silicon dioxide with negative temperature coefficient of elasticity, where the material stiffens as you increase the temperature, we can start to counteract and tweak the turnover temperatures. We're also translating our first generation of device. We use a nickel contact, which was degrading. So we're having a Schottky response, and then we're going to be transitioning to our high temperature metals. So once we have fabricated our devices, it's important to also look at the packaging. So this is another element of the technology that's really, really important. We've been working closely with researchers at University of Arkansas to study how we can take our gallium nitride chips and bond them to boards, because we might, right now we were just looking at individual elements, but one day we might want to have more complex circuits. So we need to do die attach, we need to do wire bonding. These are all important things for micro and nano electronics. And so what we do is leverage low temperature co-fired ceramic and also special high temperature pastes in order to create these die attach with electrical interconnect. And then we also do wire bonding as well, typically gold wire bonding. So then to simulate how these guys would work in a Venus-like environment, we immerse them in something called a Venus chamber. This was at University of Arkansas, and we're actually bringing one up in my group right now. And so we immerse these in a Venus condition for 10 days, so 460 degrees Celsius, 96 bar, supercritical CO2. Unfortunately, it does not have the sulfur dioxide content that you would see in Venus, so it's not the full picture. Actually, CO2 is quite inert. The sulfides are really the constituents that are really important in survivability. So these are the things we're gearing up to do at the NASA Glenn Venus chamber, and we're again trying to have these in situ tests. So we're actually working with Tomas Palacios' group to create the experimental plan so we can test these guys live inside of the NASA Venus chamber. Okay, so in our first test, this is a pre-exposure. This is a more recent version of our gallium nitride HEMT. We have our bond pads here, our titanium, aluminum, molybdenum, gold, ohmic contact, and then our Schottky contact. We've been looking at iridium oxide. So these metal oxides, which have high thermal stability, as our gate material. So pre-Venus exposure and then post-Venus, we see these oxidation effects occurring. But if you look at the IV response, pre and post, it's really interesting. I think I added a table just to summarize. We find that there's a slight increase in the saturation current. Also, our off current, slight increase, but very negligible. On-off ratio is the same roughly. Also, our threshold voltage is really staying pretty stable. And then also slight increases in our transconduction and subthreshold swing. So what that tells us is that this is working. This is a 10-day test. And so this is, in some ways working better than it did before. And so we're starting to uncover through chemical analysis what's happening to our metals. This is ohmic. This is very common. We see oxidation of the aluminum, a little bit of sinking. And then at our gate, we see the iridium oxide is not sinking. It's staying on top, which is good. So we're in the process of understanding that a bit more. I think I have about 5 more minutes or a few more minutes. So I want to get into, I promised graphene. So I want to talk a little bit about some of our recent work in graphene. And so we are thinking of, leveraging our work, not only for Venus, but for other space applications, including low Earth orbit applications. So this is work from Zach Manchester, a collaborative of mine at Carnegie Mellon. He's creating these nanosats. Maybe one day they would be made from gallium nitride, right? We have a lot of the elements, the sensing, the transistors, surface acoustic wave resonators that can be part of this autonomous system. But space environments not only have high thermal swings, they also have radiation, and there's a variety of radiation that an electronic component would see in various space environments. So it's important to really understand the environment in which you're working in. So low Earth orbit has, fairly high doses, and there can be anomalies where we have extremely high energy particles hitting your device. And these are things that you might be able to account for, or things that again, you might build redundancy in your electronics, or you can do it brute force through your materials. So one platform we've looked at is graphene on gallium nitride. So graphene is also a two-dimensional transducer, but here it's inherently through the form of the material. It's also transparent. And so we've created this ultraviolet photodetector from gallium nitride using graphene as the conductor. So these interdigitated electrodes. We've irradiated in proton environment, high energy protons at Los Alamos National Lab. These are, again, little samples here, different, each student has these samples that we put on. And then this is the graphene on GaN photodetector. So these are interdigitated electrodes. So when a photon comes in, we generate an electron, and we can measure the current, dark current, light current, and then continue to measure that over different irradiation fluences. And we see quite stable responsivity in our elements. And then also we measured the Raman profile of the graphene after the irradiation. And so this is showing the presence of the common D, G, and 2D peaks. And then after irradiation, we see this little D prime peak, which is showing, which is conveying there is some degradation in the graphene. However, nonetheless, it's still working. A couple more minutes. So we can also harness radiation as a power source. And I just want to highlight, this is a beta particle coming in, and we have excitation of carriers and recombination. And this can create current or power. So we can harvest energy from low Earth orbit potentially. And we've done this through a gallium nitride PIN architecture. This is recent work. And this, we put the pre-publication up if anyone's interested. But this is the top graphic of our device. We have a heat spreader with our P contact and then N contact as well. This is a triple mesa etch process successfully made. And Tom Heiser recently did some simulation of nickel 63, which is a radioisotope, and also an electron beam and a common SEM, scanning electron microscope, And what we find is that actually this SEM can serve to have a similar energy profile to an isotropic nickel-63 source. And so what he's showing here is cumulative energy deposition for nickel-63 versus an electron beam in a common scanning electron microscope. And so they both deposit 80% of the total energy in the depletion region, which would allow us to generate current. And so we have an open circuit voltage of 412 millivolts. So it is working as a harvester. And our devices were deployed in LEO. And maybe I'll just show one slide because I want to allow for Q&A. This is some recent work, a brand new program where we are growing graphene aerogels. So a little bit different from an electronic device, but we're growing and aim to grow these graphene aerogels on the International Space Station. Aerogels are highly thermally insulating materials. They're also used in energy storage. And we aim to grow these on the International Space Station and study the influence of a microgravity environment. So instead of turning, let's say, temperature, we can also turn a process parameter called gravity and observe how this influences the microstructure. So we're working with TechShot, our implementation partner, to create the experiment. And then we're currently studying our Earth-based samples in terms of mechanical studies and also the thermal characterization as well. So just wanted to highlight some new work we're doing in the area of graphene, but really the overarching theme of my lab is really advancing extreme environment electronics for a variety of applications. We've primarily studied high temperature operation, and then more recently starting to look at the influence of radiation-rich environments as well. So I'll end it here and happy to take any questions.
Thank you, Debbie, for a wonderful talk. We have a few minutes for questions. So if you like to type your questions in the Q&A box here on the webinar, Zoom webinar, please go ahead, do so. Or if you want to directly ask your questions, raise your hands. I'll start with one of the questions. It's asking, could one use AlGaN Hall effect plates as sensors for detecting metals in a desulfurization and upgrading in fossil fuel process? Is there bias towards a hydrogen versus oxygen centric process?
Oh, cool. Yeah, I think that, and I'm not sure what metals are used, if these are magnetic metals, nickel, iron, cobalt, but
nickel is listed.
Oh, nickel is. Okay, yeah, then that could be a way of monitoring the process non-invasively. That's what I think is really cool about magnetic field sensing, is that, it's not a probe you need to stick in there and measure, chemical concentration or strain. Maybe you can infer it through the magnetic field. And so these guys are very, very sensitive, and they're also chemically inert. So yeah, potentially those could be used in that kind of application. Thank you.
Great. So the next question is asking, could your technology be used as a photodetector to assess viscosity or emulsion in extreme temperatures, 600 to 1,000 degrees Celsius?
Ooh, what's the wavelength? Can I ask a question back?
I guess the question is from Ali Malihi. Would you?
Okay, yeah. Hi, Ali.
So let us see if we can unmute.
Yeah, otherwise I could just try to take a stab at it.
Can you hear me?
I can hear you, yes.
I don't know the wavelength. What we are doing is we have a oxy-desulfurization process that uses a catalytic process.
Okay.
We found a molecule, we mix it with titanium, and that basically softens the bonding between sulfur and carbon.
Yeah.
And then the smart bomb that hits the sulfur out or shoots it.
Yeah.
In that process, we just wanted to make sure if there's application.
Yeah, so it's interesting. I mean, you might want to look at what are the wavelengths of the emission of your sulfur process. So these have been used as, so they're gallium nitride and wide bandgap materials such as silicon carbide. Due to the bandgap, it's typically in the ultraviolet regime. So things like hydroxyl radicals, those have been sensed. And so for this process, a lot of process-based questions, which I think is interesting. So I would take a look at what radicals are formed and see if that would be something that could be measured. But yes, what would the benefit of GaN would be the inertness potentially in your environment and the ability to detect those optical signatures. But I think the wavelength you need to know.
Thank you. Thank you very much.
Okay, so the next question is asking, why did the gate leakage current jump suddenly in your transistor data?
Yeah, which one? There are multiple versions. The gate leakage is for probably the earlier one, maybe.
It's not indicating.
Oh, it's not okay. Yeah. So gate leakage, a lot of it was in the early days, just not laying out our gates right beyond the ohmic contact. So there would be some leakage around, and so there would layout effects. And then, as I mentioned, there's strain relaxation effects that can occur. So that can contribute. So we've done a lot of work in understanding the entire stack, the metals and the passivation. Actually, when you introduce oxides as a passivation layer, you get a lot of CTE mismatch, and those can translate to strain relaxation in the device. So those are the contribution, just layout, flat out like layout. Right now, where we actually have our circular hemps tend to be very low leakage, but they're larger. And so geometry, layout, and then also understanding strain.
Great. Charisse, can you please help unmute Juan to ask a question?
Hello, can you guys hear me?
Yeah.
Okay, yeah, this is Juan Herbsommer from Texas Instruments. So good presentation, Debbie. So my questions, as soon as you started talking about these devices at high temperature, the first things that came to my mind, of course, is diffusion. Okay, and this is really the bad boy here. Okay, and so many places where diffusion can kill the party here. Okay, I know that you've been focusing more into the contacts, okay, but there are many other places. For example, my question, it was more like I was thinking how your 2D gas and the interface in the multi-layers there actually is affected. And also, we do temp cycling with standard die-attached materials, and the intermetallic compounds, they just grow like crazy and become brittle die-attached, and you have the purple plague on the wire bonds, and I keep counting more and more effects here. Okay, so how do you see? I see that results that you get with 10 hours without the sulfur is encouraging. Okay, but all of these problems, has anything like you can comment about this that I'm mentioning, and how do you see this survive the more stringent Venus atmosphere at longer times than 10 hours?
Yeah, it's and I fully agree with you, and that's where the fun is actually in a lot of our contributions. I think we haven't studied the that's a good note about the AlGaN-GaN interface. We haven't noticed anything there. Certainly we've studied a lot in our ohmic and Schottky contacts, but no, we haven't gone down, and a lot of that is just inferred through our sheet density data. We see that that's been consistent. We interpret it electrically, so that conveys that the 2-deg is intact. It's not always the case. As I mentioned, the passivation actually is very important to note. But yeah, I mean, you can still see discolorization. So certainly chemical reactions are happening. And so the next step for us is really the packaging, as you mentioned, we're just getting started there what are the right coatings? You know, every device, even silicon, we have encapsulation. So that's the next step for us, but certainly a lot of work to be done.
A lot of work to do, I imagine, and I can recognize it's a big challenge, okay, because we make products and we know how difficult it is to make products just to survive, I would say, above 150 degrees centigrade. Okay, so try to do a full electronic that survives longer time at these environments are really a big challenge. Okay. Okay, thank you for your work.
And you know, some of the NASA motivations are 2 months. Right?
Okay, I know that's a big difference. We look for
it's different.
10 years,
it's like we just want the mission 2 months. So but I feel you. No,
that's
I get
important.
Totally.
Okay, thank you. Thank you.
There are many more questions, but since we're running out of time, maybe I'll end with this one. How are you identifying materials resistant to oxidation and corrosion in Venus's atmosphere?
How are we identifying?
Yeah,
it's hard. Good question. A lot of it is just digging in the literature. Like, this is kind of random, right? Iridium oxide. And we've done other interesting metals. So refractory metals tend to be inherently oxidation resistant. If you look at just metallurgy in general, right? Molybdenum is used as a chuck in a lot of heating applications. So that's where we start. And then we sort of also look deeply at the literature. What have people done? It's important to understand the chemical reactions. Again, are they inherently oxidation resistant? What is the actual resistance value? You know, are they conductive? Those are where we start. So a lot of times with the refractory, and then we just kind of just brute force test them out and see. But it does feel a lot of like, you know, chefs in the kitchen just trying things out. So yeah, that's usually really how we're doing it, kind of ad hoc.
Yeah. Right, great. So with that, just wanted to thank Debbie for taking the time to be here for a wonderful talk. And thank you to all our audience for attending the seminar. The next seminar will be on October 18th by Dr. Leo Gross from IBM Research. Thank you, Debbie, again very much for being here.
Thank you. Thanks, everyone.